for Dialog semiconductors, and we've been using UVM, or we've been using OVM for about 2 years, and subsequent to that we've been using UVM for about 6 months. So we did our first tape out in UVM, when was it? Earlier this year, January, February time, and we've got another tape out coming out at the end of this month. So yeah, so the presentation really is to do with a little bit of an introduction to the UVM Register Layer, obviously not as in-depth. It's a long topic, it would take a long time to describe in depth. Some just touching on some points to do with the UVM Register Layer, particularly in the way that we've actually deployed it, and some of the experiences that we found, really some little tips and tricks, recipes of how to do things, how we've done things with the UVM Register Layer. So yeah, so that's my summary. What are our requirements in terms of register modeling? Sorry. So what we needed, I think, previous to the use of UVM within Dialog, within my own experience, I've used quite a lot of different register models. And when we had OVM, we were using OVM RGM, we were using DIY homebrew register modeling environments that people had written in various different groups within the organization. So what the main thing that I feel that UVM Register Layer gives you is a standard modeling approach. That's the key thing. I think that all of these register modeling environments, including the homebrew stuff, will do the same kind of tricks that you wanted. But since there's been a transition to UVM within Dialog, this is one of the key benefits that we think is that we'll all move to a standard modeling approach for that. One of the particular requirements that we had for these particular sort of series of ICs that we've been doing was to have, we have distributed register blocks in the IPs within the SoC. We have a very sort of field-centric unit of storage in there. So basically the access policies inside the design are on a field-by-field basis. That's one of the requirements that we had to have. Obviously these register modeling packages need to support that. And as everybody would say, we have a lot of non-standard quirky registers, as they say in the UVM parlance. And I'm sure that most people that do designs with registers in them would say that the basic register modeling capability that you get off the shelf isn't enough to model all those extra side effects or quirky behavior that you actually have in your design. So the sort of things that we had is we had a locking mechanism that's dependent upon the busmaster, the idea of the busmaster that's accessing a particular register, which is locked out by another one. We have a coherency between registers, so we have a register access which will create another set of registers which are associated to be sort of snapped in a pipeline, snapshot generation. We also have this classic stuff which is interrupted event generation. And the other more complicated sort of scenario we had is that we had to, all of these registers were generatable from our sort of library of RTL generation sort of kit that we've got, and all these functionalities can be layered on top of each other. So that means we need to be able to capture the quirky behavior, but also layer it and add these at will, add them, these different behaviors at will. And the other requirement is that we have the need to run our UVM environments in other directed chip-level environments. So it's not good enough for us to have this thing reliant upon a UVM reg sequencer all the time to make it work. So we have to have a mechanism of updating and checking the register model in our UVM environment, which is passive, works in a passive mode. Okay, so that's one thing that we had to do. And we had some issues certainly over implementing that in the UVM 1.1. And the final thing, which I think everybody would have as a standard requirement for any register generation, register modeling, is that it has to be automatically generated, because you can't hand enter all these, the register classes. That all has to be automatically generated from your spec, which in our case is a spreadsheet. So what does the UVM register layer give you? I use the name UVM Reg. I think that's one of the things that you'll see in the literature. People tend to call it UVM Reg or UVM Register Layer. It's an abstract model for the registers and memories in the DUT. It maintains a mirror of the DUT registers. So it's mirroring the behavior of the DUT registers based upon observations around the bus of the DUT or other side effects that you might bolt into your reference model. So the hierarchy inside the UVM Reg that's available to you is that you can build a hierarchy within there that's analogous to the DUT. So you've got this sort of container, structural container called the UVM Reg block, which can contain other UVM Reg blocks inside it, or UVM memories, or UVM registers which are composed of UVM reg fields. So we've got a very hierarchical organization that we can build up. But one of the points to note about this hierarchy is not actually a UVM component hierarchy, it's actually a UVM object hierarchy. So although there's a build method in there, it's not related to the UVM phasing. So you build it in a hierarchical way, but you don't use the standard UVM phasing. The other main thing that it gives us is the standardized register access API. So obviously you don't want to have to access your registers based upon their address in the address map, because that could change, or you might have new registers going in there. So it's address independent access to your registers via instance names within that hierarchy, or else via string names, which is preferable. And the other functionality that it gives us, which is interesting to us, and I guess to a lot of people, is that you can put into a register block multiple address maps which represent different physical interfaces into that model in the real design. So, for example, if you've got something like a dual port RAM, or you've got a memory which has got part of it accessible to one bus master, another part of it accessible to another bus master, or the registers locations are aliased for different accesses on the different physical interfaces, then you need to be able to model that. And that's how you do it in the UVM Register Layer. So this is, I've drawn a picture of really what we did in our register modeling, the components that we put in. There's lots of ways of using the register modeling layer. And this is the way that you'll see if you look into the literature, is the kind of the explicit predictor mechanism. So we can separate on the left-hand side of the slide, the active part, which I wish to be able to use sometimes and other times not use, and for the whole thing to carry on working. So I've got my user sequence, which is a test sequence doing some register accesses on the left-hand side. It's using the register access API that you get with your UVM register model. So we're doing reads and writes to either registers via a hierarchy name on the left there, or by name. We can get a register by name out of or a field by name out of the register block. Then what happens is the API goes in, you call into a register that's instantiated inside your register block, and that will in turn use this register map to select a particular adapter, which represents a transformation from a register operation to a physical operation on your bus. So then that will then cause a sequence, a mini sequence or a sequence item to be generated, because you have to hook that up into your agent, and that will then drive the physical register access onto the bus. So that's one part of the picture. The second part of the picture is we wish to maintain this mirror of what's happening inside the DUT. So separate to the driving channel, we've got a monitoring channel on the bus, which is on a bus agent. We've got a monitor with an analysis port on there, and an analysis export on the UVM Reg predictor, which uses a hook into the same adapter component that we've created. And that will actually transform an observed bus transaction back into a register operation, and then it will set the register map according to what it's just seen on the bus. So that's the basic kit of how we would just do a dumb mirroring of what's going on inside the DUT to what's going on inside our. So there's a bit more complication than the simple mirroring, because within what was slightly confusing for me to start off with, looking at this register modeling packages, there's a kind of deferred update mechanism that's inside there as well. So you can have this kind of pipeline between the desired value and the mirrored value. So you can actually set a desired value for the register in the DUT, and then at some point later in time, you can call an update. You can do that on multiple registers actually inside the model, and then call an update, and it will just fire off all the physical accesses it needs to do that. And similarly, you can mirror back. You can say, well, I want the mirror value to be the same as the DUT, and it will actually read and update the model value according to what you want. But actually, those things weren't of interest to us in what we were trying to do. So what we were trying to do is just maintain the mirrored value. So the sort of the methods, the API methods in red there, the write, the read, the get, and the predict, are ones that essentially bypass the notion of having to have a pipeline between desired and mirrored value, because in those cases the desired value is always the same as the mirrored value. So the writing will actually generate a physical write to DUT, the read will generate a physical read, gets the desired register from the model. So for example, when you've got a reference model, you need to know what a register is doing in the design at a particular point in time. You can just get out what it is. And if you have a side effect that you observe something in your scoreboard or something in your verification environment which necessitates the change of a register in your model, then you use this predict method to change the. This is how we created our register model. So what you could do, in fact, what I actually started off doing is we put some register classes in by hand, and you work out how you're going to do this, and you get somebody else to automate it. So our sort of source of information is we have a specification, we have a design specification in a spreadsheet, part of which is a register specification. We use this open source library called Template Toolkit, which actually will allow you to generate any kind of code, really. So we use it to generate documentation, system Verilog code, RTL code as well. But obviously there are other open source tools, there's commercial tools to do this sort of thing. You can actually generate your register model with Spirit description and use some of the, I think there's some register generators that you can get that are probably provided with the UVM, or you can certainly get them from the vendors. So basically somebody needs to create a register model. Part of that is the description of how the registers work. So you'll see that you've got a field configuration method there, which basically says things like how big is this field, what's the LSB, what sort of access has it got, the access policy, read only, write read, this sort of stuff, is it volatile, the reset value, etc., etc., etc. So that's how you create the class for your register model in terms of the fields. A register is a collection of fields, and then what's not shown on here is another thing that we obviously had to do, is that UVM Reg doesn't give you any coverage implementation at all, so you have to create your own coverage model inside the register classes that you're generating. What it does give you is it gives you a register, gives you a coverage API, so you can say, you can basically switch on or off coverage. You can expect whether the coverage has been switched on or off, and also there's various levels of coverage that you can define, whether you're going to cover the bits of the register, the value of the register, the address map, etc., etc. So we did use that, but you just bear in mind that you need to create this. This isn't given to you as part of the register layer. So what you get for free is a simple model that is talking about the access policies. So it's dumb storage subject to one of 25 predefined access policies, things like read, write, clear on read, set on read, write, read, clear. I don't know what that does, but these sort of things. But actually most of our registers are more quirky than this, to coin the phrase. And if you want to capture that more complex behavior, then what you need to do is you need to basically override methods which are defined in some callbacks, which are part of the register layer. So the idea of a callback is something that's basically been inherited from the VMM library, and it's something that you can actually add at runtime if you really want to, but it basically gives you some hook methods that get called at specific times of the model update. So, for example, you can see that we've got hook methods that will get called just before a read happens, just after a read happens, just before a write, just after a write, and after a predict has happened on a register field. So for us, we need to model put all our quirky behavior in the post-predict callback, because we need to make sure that we are updating our model based on observed bus transactions rather than something that's explicit, because we're not always necessarily using the read and write methods from a sequence. So we want this thing to passively update the register model and keep it in tune with the DUT and all the quirky behavior. So here's an example of really simple control field. This is the actual thing that we have in the design. It seems a bit simple, but simplistic in textbook, but it's actually something that we have. It's a simple 2-bit control field. So you write a 1 to set it and you write a 2 to clear it. So what we do is we just have a very simple bit of code. We override this post-predict. We create a derived class from the UVM Reg TVS, UVM Reg Callback class. I've called it control reg field here. And we override what post-predict does. So if it's seen a write, if the kind of the access has been a UVM predict write, and the value that was written here, the value that we've seen, the current value of it, if it was set to a 1, yes, that's fine. If it was a 2, yes, we clear it. Otherwise, we do nothing with that value. We set it back to the previous value. So that's an example of how we have to capture this sort of quirky behavior Another example was to try and implement a sort of locking behavior. So it's a little bit more complicated in that we had to actually create a callback, and when you actually instantiate that callback, you have to give it the name of a locking field. So the functionality we're capturing here is we have one field in our register map which is capable of locking a number of other fields in that map, and it has a predefined string name. Okay. So when we build a register model, we add these callbacks into it, and we give it in the constructor, we give it a lock name here for this callback. So here what we do in the post-predict function is we say, okay, if we've seen a write, we'll actually run through a bit of code down here. We won't go through the details too much, but basically we get all the fields from the map, and we look for a field with the same name as the lock name. And if that lock name, the value of that, which we get back with a get function, if that's non-zero, then yes, we're just going to say value is equal to previous. And what that means is just don't set the value. So we go back to what it was. Right, we're going to have to hurry this one up, I'm afraid. I've only got 4 minutes to go. Here's an example of a recipe of how you might model status registers. So, for example, we've got something here which is defined as having a read-only access policy, but actually what we want to do is we want to update that register in our model whenever something happens inside our environment. So this is a real-time clock count, for example. So what we do is we just, in our scoreboard or reference model, we just simply call the predict method. Here we're sort of showing it incrementing a count and setting that into the contents of that register. And the important thing to say about the predict is it actually bypasses any access policy. So in this case, the read-only won't be honoured, and it just sets the value straight away. So that's the important thing to say about that one. Another sort of issue that we always seem to have with register models is that sometimes we don't know exactly when a DUT register will change. We sort of have an uncertainty window around it. And one of the ways of dealing with this is we don't really want to go down the route of creating necessarily cycle-accurate reference models. One of the ways of dealing with this is to basically say, well, if a register read happens at this time, we don't check it in our scoreboard, or we don't check it in our register model, we don't update the register model because we've already set what we expect it to be in the register model here. Sometime later, we know the DUT is going to set it, but during this uncertainty period, then we want to actually suppress any checking or updating. So here's the boilerplate code, and here's the code of how we might do it. At the end? I'm trying to hurry up.
I gave you a warning.
So just a point to say here is that you can set comparison. It's possible to set comparison on a register field with this set compare method. So on a field by field basis, you can say, okay, don't check it. But what you also need to do in this instance is to actually prevent update as well. So this is what we do in this register, extended register field class. Yeah. Okay, fine. That's quite a good one. But what I'll do is just go. I'm just going to wind straight onto the conclusions because I think Mike said there's only about a minute or so left. Just quickly recap. Then I think the register modeling standard is key to UVM. I see that personally. I think it's a key part of the UVM standard. We personally had an inconsistent approach to register modeling with OVM. UVM Reg has all the features necessary to do it, albeit I wouldn't say it's any better or worse than anything else that I've seen. Except to say that with 1.1, I did have a lot of issues because the passive compare and update wasn't supported. So I actually had to create a separate register checker component in the environment. There was also a lot of bug fixes done in a lot of bugs around the register modeling, about 20 odd, which we fixed in 1.1a. So that's my recommendation to use 1.1a. And the other thing to say is that there's a different kind of paradigm going on here with Quirky register modeling from the standard OO extension that you might be used to. So it's a different concept that comes in that you must become familiar with. And it can be quite complex if you're sort of layering behaviors, which is what we had to do. Good examples in boilerplate code. I've used the Verification Academy to start off with just to, for the boilerplate code of how to actually integrate it into the environment. It's fine, it's great. Okay, that's the end of my presentation. Right, okay.
Any questions?
Yes, the primary model which we've compared is the thing that's created by our TTQ script, which is the UVM. of it. That's our primary model. Yeah, so you're comparing that. That's the spec is generating the register model of classes. When the DUT is in a simulation, then you're checking against that by this prediction and readback mechanism. So you're actually checking to half of the prediction, which isn't shown there, is it's doing a check against the expected value.
Just quickly before we finish, a quick thank you to our speakers again. That's John Ainsley of DULOS, Steve, who's just given a talk on register accesses. Just to say, and we did rush Steve a bit, but all his slides will be online fairly quickly, hopefully this afternoon. We'll send out the email so you can get those slides if you want. That's Steve Holloway from Dialog, and also Manish from India. Those slides will be available online as well. Quickly, just before we go, a quick advert, not for DVClub, not for TVS. The next one is on the 2nd of July. Topic to be discussed. And verification futures, we're very pleased that verification futures was so successful in last year, where we had 300 people, 100 organisations in 21 different countries. And this year we're going for European dominance. So as you can see there, we're travelling around Europe. We're going to get T-shirts with these places on our back. So 19th of November, we've got a full day in Heathrow. 21st is a full day in Grenoble. 22nd is a full day in Munich. It's all on that link, but we'll send that email out. It's free attendance again. Our sponsors, our CAD vendor sponsors, kindly pay for this. So it is free attendance again. And also around those events, there'll be some training sessions as well. So I know a few companies are putting on a training session either side of those events, so that you can turn up one day for the conference and stay a second day for some training. I think that's it. Any questions for Bristol? Otherwise, we'll see you in July. Once again, thank you for our speakers. Thanks, Steve.